Okay, so when we left off, we were finding the time for bike A. It's going to be 1600 meters divided by 8 meters per second. So the time that bike A needs to finish the race is 200 seconds. So if B is going to catch A right at the finish line, it means B also has 200 seconds. So now we can find the VAV for it. Delta D over delta T. So 1827.27 divided by 200 seconds. So Buddy, if he wants to catch the other person right at the finish line, 9.13635 meters per second is how fast he needs to go. So hopefully that one was pretty simple. Number 4. Number 4 are car A and B traveling to the right. A is behind B. So here's A. Here's B. Okay. A is behind B 6.096 meters. They are both going 96 kilometers per hour, which is 26.6 repeating. So VI is 26.6 repeating meters per second for both of them. Okay, it says that B begins to slow down at a rate. So the acceleration of car B is negative 7.3152 meters per second. How long will it be before A hits B? A doesn't slow down. Okay, A's drinking his ice cap or her ice cap, listening to some tunes, checking text messages, doesn't know that notice that B stepped on the brakes. And so A doesn't slow down, and so the question will be, when is A right up here where B is? So B is going to travel some distance in that time. A is going to end up at the same spot, which means A's distance is going to look like that. So it means that you're looking for delta dA, which will be equal to delta dB plus the 6.096 meters. This is really then a VAV for A. So delta dA is just going to equal VAV delta T. Okay, so this will be VAV delta T. The times, of course, will be the same. For B, delta dB will equal VI delta T 1/2 A delta T squared. So down here, VI delta T 1/2 A delta T squared. And then, of course, we have the 6.096 meters. Now, this might look yucky, but it's really not going to be that bad because the VAV and the VI delta T are the same. And so they're going to cancel out. We bring our 1/2 A delta T squared over to this side. It's equal to 6.096 meters. Multiply by 2 and divide by A, and you'll have, and take the negative over. T squared will be equal to negative 2 times 6.096 meters. You might get a little panicked over that negative, but remember the A is negative, but he's slowing down. So negative 2 times 6.096 meters, and it's going to be divided by negative 7.3152 meters per second squared. So now do the math. The two negatives cancel. 6.096 times 2 divided by 7.315, and you get 16, take the square root. I think I got 12.91 seconds. So delta T is equal to 12.91 seconds. Now you can take this, plug it in up here, plug it in up here, and find out how far both of them fell. Because it asks, oh, it doesn't even ask that. It just asks time. Okay? So that's number 4. Number 5, Willie and Millie. Now, I should probably tell you that Willie is Millie's younger sibling. And like any younger sibling, tends to like to aggravate the older sibling. So Willie is looking out this window that has this little lid and just happens to have this flower pot on it. And Willie sees Millie standing down below and thinks, ah, I could knock the flower pot off on her head. Of course, after he does it, he realizes, oh crap, am I ever going to get in a lot of trouble if that hits her? So he decides to yell to warn her. But he doesn't want to yell too soon, because what fun would that be if it wasn't close? So he wants to figure out what's the minimum height. How long can he wait before he yells to warn her? Okay? So that's what the question's asking. So it says the window is 35 meters above the ground. And it says Millie is a total of 1.05 meters tall. But her ears are a measly little 5 centimeters below the top of her head. And that's going to become important when we talk about the sound. Because there's two things. There's the flower pot falling. And then there is the sound going down. For the flower pot falling, we know VI is 0. We know that A is 9.81 meters per second squared. And the delta D, it's going to hit her on the head. So the delta D is 35 meters minus the 1.05. So it's 33.95 meters. Okay? For the sound, it tells us the speed is 340 meters per second. And the sound actually has to travel all the way down to her ears, so it has to travel 34 meters. It also tells us that Millie needs a 0.4 seconds to respond, so her reaction time is 0.4 seconds. Okay, so from this one you can find the time it takes the pot to fall. So delta D is equal to VI delta T, 1/2 A delta T squared. This goes to 0. T squared is just going to equal 2 delta D over A. So 2 times 33.95 meters divided by 9.81 meters per second squared. And then, of course, you're going to take the square root. So 2 times 33.95 divided by 9.81. Take the square root, and you get 2.63088 or 76. So don't round too much here. Okay? Once you have that, you can also find how long it's going to take the sound to reach her. Because we know VAV is equal to delta D over delta T. So delta T of the sound, so this is for the pot. Delta T of the sound is just going to be delta D over VAV. So 34 meters over 340 meters per second. So delta T for the sound is going to be 0.1 of a second. And then delta T of Millie is 0.4. So now the question is, what the heck do you do with all these times? How are they connected? This is the part you have to stop and think about. Okay? So it's going to take 2.63 seconds for the pot to get to her. But then if you want to warn her just in time, you need to leave her 0.5 of a second. Right? The 0.4 plus the 0.1. So take 0.5 of a second off of this time. And it'll be 2.61088, etc. seconds. Now use this time to find out where is the pot after that. So go back to delta T of the pot and solve using our new time. VI will still go to 0, so delta T of the pot will be 1/2 9.81 meters per second squared times this 2.61088 seconds. You have the other decimals. Don't round them in your calculator. Just subtract 0.5 from them. Okay, so square the time. Oh, I don't know what I just did, but I did definitely screwed up after me saying that. 2 times 33.